Okay, the example I'm going to use to illustrate ARIMA modeling with non-seasonal data is one taken from a textbook by Walter Enders called Applied Econometric Time Series. Now, the example starts on page 89 of the third edition, if you want to check it for yourself. He attempts to estimate and forecast data on the interest rate spread between US government bonds and treasury bills. So first of all, reading in the data here, which you can get from Walter Enders' website. I'm now going to turn this into a time series object, a matrix time series. It's, as you can see, quarterly data beginning in 1960 quarter 1. I'll now use the two variables in there, R10, which is the bond rate, 10-year bond rate, and T-bill, to create the interest rate spread variable. So now I have the data which Enders himself uses. Plotting it, we can see what it looks like. Now it looks reasonably stationary, and indeed Enders concludes that it is by looking at the ACF and PACF. Now to show those, I'm going to load up firstly the forecast package, which is the package I'm going to use here, which is an excellent package for ARIMA modeling and other time series forecasting. And using a function in there called ggtsDisplay, gg meaning it uses ggplot2, you get a nice combined chart showing the data again, plus the ACF and PACF. Now Enders uses those to determine several candidate models, and I'll show how to estimate some of them. So beginning with an ARIMA 700. Now again, I'm using the function ARIMA with a capital A in the forecast package. There is a built-in function ARIMA with a small a, but this one is better. So you simply use ARIMA with firstly the parameters are firstly the data set spread. You then put order equals, and as a vector you put the values of P, D and Q, 700 in this case. Notice D is 0 because Enders concluded that the data was stationary and didn't need differencing. Now in order to reproduce the results in Enders, you have to specify the method as CSS, conditional sum of squares. If you don't specify the method, it will use a default method which is different, and you'll get slightly different results. So here I'm wanting to replicate Enders results and specifying method equals CSS. That's not to say the other methods are wrong, simply that this is the one that Enders uses. So running that, and then simply printing it out. You get the printout of the results. What you get here in fact is the coefficient estimates and the standard errors. No t-stat, but of course the t-stat is the coefficient estimate divided by the standard error, so you can work those out. You also get an estimate of the mean of the data rather than the constant term. Enders reports the constant term. Now it's possible to recover the constant term by simply multiplying the mean by 1 minus the sum of the other coefficients. So I've done that here. I've used the coef function to recover the coefficients, and I'm using the 8th one, which is the mean. Then I'm multiplying that by 1 minus the sum of the other ones. So it's all the coefficients minus the 8th one, so that's the sum of the 7. And you can use that method generally if you want to find the constant term, although it's not strictly necessary. So that gives me the constant of 0.210, so the same obviously as Enders. Now to calculate the various goodness of fit, I'm going to first of all find this residual sum of squares here, using the residuals function on AR7 to recover them, square them, and then take the sum. Now you can calculate the AIC, which is one of the other measures of goodness of fit, of course, using the standard formula. Again, you'll find this formula in Enders' text or in other texts on ARIMA modeling. So running that, and then you can find the SBC, also known as the BIC, again using standard formula for that. Notice the number of observations here is 186. There's actually 193 observations in the whole data set, but of course when you use 7 lags, that means the first 7 observation periods are effectively dropped, so that's why it's 186. Now the other thing that Enders reports for each model are the Young box test statistics for 4 lags, 8 lags and 12 lags. Now, this of course is a test of joint significance of a group of lagged coefficients on the residuals. Now the best way of doing this, finding these in using the focus package, is with a function within the focus package called check residuals, which will plot the residuals themselves plus the ACF plus a histogram, and also carry out the Young box test. Now the syntax is easy. It's check residuals, then in brackets the inputs are the object containing the model results, AR7 in this case, comma, and then the number of lags you want to check. So first of all 4. So as you can see, we get a nice, first of all, a chart, a nice combined chart with the plot of the residuals, the ACF of the residuals, and a histogram to check for normality. In fact, you'll notice here that we get this warning message. As you probably know, and you'll find this in the text, when you run the Young box test on the residuals, of course it's a chi-squared statistic which it produces. You then have to, of course, compare that test statistic with the critical value, and in order to read off a critical value, of course, you need to know the degrees of freedom of the test. Now, in the case of residuals, the degrees of freedom is equal to the number of lags that you are checking, in this case 4, minus the sum of P and Q plus 1 if there is a constant. Now in this particular model here, I'm checking 4 lags, so total lags used 4, but what it calls the model degrees of freedom, P plus Q plus 1, is of course 8. 7 here, P, 0 for Q, and then there was a constant, so that's 8. So that's what it's specifying there. Now of course that gives you a degrees of freedom for the test of minus 4. Well, that's no good. You cannot find a critical value from chi-square distribution with minus 4 degrees of freedom. The lowest is 1, which is why we don't get any p-value here. So what I'm going to do here is to use Q chi-squared, the chi-squared distribution that's built into R, the function, to find the critical value. You could obviously read it from some tables, but you can do it within R itself. So I'm using Q chi-squared and then in brackets 0.95 to give me a 5% or 95% significance level, comma, and then 1 degree of freedom. So I'm finding the critical value with 1 degree of freedom, which is the nearest, the lowest that you can go, which gives me 3.841. Clearly our test statistic is well below that, indicating that this test of the correlations on the residuals are jointly significant from 0 is not rejected. Looking back at the ACF, that's not surprising. The first 4 here are all well within, individually insignificant, so collectively they are as well. Now if I want to check 8 lags, which again, if you look at the individual ones, they all seem okay, so that would probably be okay jointly. I can use check residuals again, this time specifying 8 lags, but notice I've also put plot equals false because I don't want this to be, this combined chart to be plotted again. I've got it once. So that gives me just a Young box test. Now again, there's a problem here because 8 lags minus the 8 degrees of freedom in the model gives me 0. Well, again, you cannot find a critical value with 0 degrees of freedom from a chi-squared distribution, which is why this p-value is rather odd. So again, I'm going to find one using the q chi-squared function for 4 degrees of freedom, which is 9.844, and again that's well within that, so the test for 8 lags seems to be okay. Let's find finally the other one which Enders reports, which is the for 12 lags. This time there's no problem, of course. 12 lags with model degrees of freedom of 8 gives me degrees of freedom for the test of 4, so it's able to look up a critical value and find the p-value, and you notice that is rejected at the 5% level, although it's okay at the 1% level. Looking back here, that's probably because of that significant one at lag 11. But overall it looks as if the residuals for this model, ARIMA 700, are fine, they're white noise. So this is a potential model for forecasting. Of course, there may be other models that also have white noise residuals, and you can choose between them by looking at the AIC or the SBC. Okay, let's look at how to estimate another of the models that Enders looks at, ARIMA 201. Now, it's exactly the same here as here, of course, using the ARIMA function. So that's going to be very, very similar. There's a key difference, however, and that's which I need to point out. You notice here that the data I'm putting in is not spread, not the whole data set, but a subset of that, which of course you can create using the window function with time series data. And the reason for that is that, as Enders emphasizes, if you're going to compare different models and decide which one's best for forecasting, then in order to compare the AIC and the SBC, you must estimate the models over the same sample period. Now, for this one, of course, the data goes from 1960 quarter 1, but because the first 7 observations are effectively dropped when you use 7 lags here, the sample period was in effect from 1961 quarter 4. So I need to make sure that's the case here. Now here we're only putting in 2 lags, autologarithmic lags, so that means that we need to start the period here of data, start the data from 1961 quarter 2, so that when those first 2 are effectively dropped, you then again effectively run the estimation from 1961 quarter 4, the same as this one. So you need to work out here where you need to start the data in order to make sure this is run over the same 186 periods. So apart from that, everything else is the same. I specify the order, 201, method CSS, so we can quickly estimate this model. Sum of square residuals, AIC, SBC. Now I can check the residuals for white noise. So that gives me the plot. Again, a slight problem here in that because I'm checking for 4 lags and there are 4 degrees of freedom in the model, notice this time 2 for P, 1 for Q, that's 3, and 1 for the constant, that's 4, and that ends up with a degrees of freedom 0, which again is not possible. So you would need in fact to find a critical value yourself. I already did that up here for 1 degree of freedom, and in fact we got for that 3.84. So that again is clearly well within that. So that test is not rejected. Looking at the plot, that's not, again, not surprising. Even the first 4 here are fine. Let's do it now for 8. Here there's no problem now with the degrees of freedom. 8 minus 4 is 4, so we get a proper p-value. Now that is less than 0.05, so at the 5% level it's rejected, but not at the 1%. So that's again probably because of that 7 flag here. And then let's do the 12. And that clearly is rejected at the 5 and 1% levels. So there is a, again that's not surprising there, there's 7 and 11 individually are significant, so collectively that one is rejected. So there's a potential problem with the residuals on this ARIMA 201 model, so it doesn't appear to be as good as the ARIMA 7.0.0. Okay, so as you can see, using the ARIMA function, capital A, RIMA, the ARIMA function in the forecast package and the check residuals, you can easily estimate these models. Now, in fact, as you'll find if you look in Ender's text, he does estimate some other models which are, in a sense, slightly non-standard, and by which I mean that he looks at models where there are gaps in the lag structure. For example, he estimates a model here 2, 0, and then you notice I've got in brackets 1, 7. In other words, 2 autoregressive elements, again obviously no difference, but then on the moving average part he has a moving average element at lag 1 and then at lag 7, but nothing in between. So it's not 7, we're not saying that there are 7 moving average elements here, there are 2, but they're spaced apart. Now you can't estimate a model like that with the ARIMA function here in forecast. It won't do it. It will only estimate ones where there's no gaps in the lag structure. If you want to estimate a model like this, then there is a package called T-Series here, which will enable you to do that. And the function in there is simply called ARMA, A-R-M-A. So I'm going to load up T-Series. Now, in order to estimate, the syntax is slightly different here from the ARIMA function. So it's ARMA, then in brackets obviously spread the data here, and then lag equals, and then it's a list. So this is how you specify the model. You put lag equals list, and then in brackets you include 2 elements in the list. One to specify the auto-regression element, so you put AR equals and then a vector. So in this case I want, notice you don't put a 2, you have to put 1, 2 to list the actual elements. Now for MA, again, the same, equals and a vector and 1, 7. So you notice this does enable you to specify here where there's 1 at lag 1 and then 1 at lag 7, but nothing in between. By the way, if there are no moving average elements, you put MA equals null. Okay, so as you can see, the syntax is slightly different here because you have to use a list, but it does enable you to estimate models of this type where there are gaps in the lag structure. So I can run that, print out the results. In this case, you need to use the summary function to do that. So here, in fact, you get rather more detailed. You get the coefficient. This time you do get the intercept rather than the mean. And this time you do get the t-values. Now it gives you an AIC here, but this is different from the one that Enders reports. It must be using a different way of calculating it. To get the ones that Enders reports, you need to calculate it manually, as I did before. Now let's see how, first of all, to get the residual sum of squares. Okay, now there's an important point here in that you can use the residuals function to recover the residuals as before and then square them, but before you sum them you have to make sure that you omit missing values, because if you look at the what is it, AR, that's the one, yeah. If we look at this list here showing the results, and you look at the residuals, notice that it uses the whole 193 observations, or reports that, but the first 7, of course, are missing because of the structure we put in. So if you don't tell it to omit those missing values, you're not going to get the right answer, because it's not going to use just the 106 actual values. So this is why I had to put na.omit there around this residuals function to omit those. So that gives me now the sum of squares. I can calculate AIC and SBC in the usual way. Again, 186, again, must be over the same sample period. Now, if I use check residuals here, I'm simply doing this to get the graph, because it won't actually work. Since it's from the forecast package, it only works on the ARIMA function from the forecast package. It won't work on the results here from the T-series function, but it will give you the graph, the ACF and so on. So to actually run the Young-Box test here, you need to use the box.test function on the residuals, again making sure you omit the missing values, so you only get the 186 that count. So then you put lag equals and specify the number of lags. In this case I'll just do the 12 lag one. Obviously you could put 4 or 8. Make sure you tell it the type is Young, and also here you must tell it how many degrees of freedom the model has, so that those are subtracted. Now in this case it was 5. 2 here, another 2 there, plus the constant 5. And that will give you the correct p-value. So we run that, and as you can see it's used 7, which is correct, 12 minus 5, to give me a p-value. Now that is not less than 0.05, so at the 12 lags seem to be okay. Look back at the ACF, as you can see, they're all okay. In fact, lag 11 seems to be significant, but taking all 12 jointly, that's okay, and certainly almost 4 and 8 would be okay. I haven't run them here, but probably fine. So this, in fact, model does appear to have white noise residuals. It's a candidate model. To compare that, therefore, with the ARIMA 700, you could look at the residual sum of squares, or the SBC, or the AIC, to decide which one maybe is best. Okay, so that shows you how to do some ARIMA modeling using in R. I will mention a couple of other things finally. It turns out that the forecast package actually has an automated ARIMA procedure built into it, which will carry out all this kind of analysis here, checking for stationarity, estimating different models, comparing them, checking the residuals, all automatically by using just one function called auto.arima. So this is a shortcut way of carrying all of this analysis in a much quicker way. However, the danger with this auto-page procedure is that it doesn't allow for detailed comparison of different models, and because it's from the forecasting package, it won't allow you to estimate models of this particular type here with gaps in the lag structure. And there's no guarantee, therefore, I suppose, that it will give you necessarily the best model. But then again, it may work fine. So let's run it. It's very easy. Auto.arima, the data set. Again, I'm specifying method CSS so that it uses the same method as enders. So if you run that and then print it out, as you can see, the AutoArima function has first of all decided that the data is not stationary and needs to be first different, so that's clearly different from what enders concluded. And it's also determined that the best fitting model has two autoregressive elements and two moving average elements. So it's an ARIMA 212 model is what it comes up with. Now that's not what Enders concludes as being the two best models. Enders concludes the two best models are the ARIMA, the ones I've done here, ARIMA 700 and this ARIMA 2017. So if you use the auto ARIMA, then you're basically assuming that it's going to give you the best model, but it may not. If we check the residuals on that model, then you'll see that if you look at the residuals, there does seem to be a potential problem here, maybe with the 7th lag there and the 12th lag. So it's kind of surprising in a sense that it chose that. If we look at the ring box test, that on 8 lags again does seem to be a problem. So I can say it's kind of surprising that it chose that model. Now, again, finally, let's look at forecasting. Now, the advantage of using the ARIMA function in the forecast package here is that this then enables you to use the forecast function to create the forecasts and to plot them very neatly and quickly. So I'm going to show you I'll show you how to do that here. Notice here, by the way, that I've used the pipe. I haven't used the pipe up here, but as you're aware, using the pipe operator is becoming very common in R as a way of entering multifunction code, because it's much more readable rather than using functions within functions or intermediate variables. I've done a video on this, which you'll find on my site. So here I'm taking AR7, then I'm forecasting that. So the input to the forecast is simply the model here, AR7, and then I'm using autoplot of the results of the forecast function, the forecast in other words, to plot them. And in fact this autoplot also plots the actual data and appends the forecast to the end with prediction intervals, as you'll see. So let's run that. And as you can see, you get a very nice chart here using ggplot of the data together with then the forecasts here, and prediction 95 and 99% prediction intervals around that. So it's very neat. And if you want to improve the labels here, you can do that in the usual way. So let's forecast the AR2MA1, the ARIMA 201 model, which I estimated. And, as you can see, slightly different forecasts from the ARIMA 700. And let's finally forecast the model that was chosen by the AutoARIMA function. Again, that's more similar to the ARIMA 201, I should say. Here's the 201, this is the ARIMA 212, very similar. Okay, so that is a quick run through of how you can do some basic ARIMA modeling with non-seasonal data in R.